Greetings to the respected faculty. Today, I'll be talking about graph terminology, a practical guide as a part of the course Essentials of Problem Solving. My name is Lasya Mandapati and I'm from CSC AI&ML B section. My roll number is 24951A6686. Graphs are an essential part of computer science, mathematics, and many real world applications. From social networks to GPS navigation, graphs help us understand relationships between objects. By the end of this presentation, hopefully, you'll have a solid grasp of graph terminology and its uses. Let's dive in. So, what exactly is a graph? In simple terms, a graph is a collection of vertices or edges. Vertices vertices or simply nodes represent objects. Edges or links represent connections between the objects. As you can see in the picture, the vertices A, B, C, D, and E could be separate objects that are linked by relationships or connections that we are representing through lines called edges. So where exactly do we use graphs? Consider Facebook. E- uh, for example, in Facebook, essentially each user is a vertex, and the friendship between two users is an edge connecting them. Another example is Google Maps, where locations are nodes and roads connecting them are edges. As you can see here, we are considering a podcast, where a podcast can be related to another podcast. And as you can see, for example, your podcast is horror. It falls under the category of horror. And people, if I talk on the podcast, it's owned by me. And every episode that is published under the podcast is also authored by me. So hence you can form the connection here. And there's also a picture of a simple graph. So we can understand that so we can see that understanding graphs helps us solve real world applications much more efficiently. Graphs come in different types. The first distinction is between directed and undirected graphs. In an undirected graphs, edges have no direction. For example, friendships in social media. If A is friends with B, then B is also friends with A. In a directed graph or digraph, edges have specific direction, like Twitter followers. If A follows B, B doesn't necessarily follow A. Another distinction is between weighted and unweighted graphs. Weighted graphs have numbers on edges representing distances or costs, like Google Maps. Unweighted graphs treat all edges equally. These variations allow graphs to be applied to different real-world applications. As you can see in the picture, they represent undirected, directed, and weighted graphs. Now, let us discuss some essential graph terms. Vertex. This is represented by V and is also called a node. It's basically a point in the graph. It is used to represent objects. Edges, simply represented by E or an arc. It is a line connecting two vertices and represents connections and relationships. Degree of a vertex, or simply DEG of V, the number is basically the number of edges connected to a vertex. Adjacent vertices. These are two vertices connected by an edge. For example, in a city road network, intersections are vertices, nodes are edges. If a crossroad has four connecting streets, its degree is 4. These fundamental terms help us analyze graphs mathematically. A few other terms would be isolated vertices. Essentially, these vertices have no edges and are not connected to any other nodes. Self loop. Here, the edge connects the vertex to itself. A simple graph. There are no self loops and no two edges connect the same two graphs. As in A connects to B and that's it. B does not essentially have another edge that connects B to A. A multigraph. These graphs have multiple edges connecting the same vertices. That is essentially A is connected to B through 3 or 4 or multiple edges. Pseudograph. These are basically graphs that contain multigraphs and with self loops. Certain graphs have unique structures. A complete graph K of n has every vertex connected to every other vertex. For example, in a small team where everyone communicates with everyone, the communication network forms a complete graph, a bipartite graph. This graph divides vertices into two sets, with edges only between them, such as job matching between applicants and companies. A connected graph ensures all vertices are reachable from any other vertex, while a disconnected graph has isolated paths. These classifications help us understand different relationships and their applications. A path in a graph is a sequence of edges connecting vertices. A simple path never repeats a vertex, while a cycle is a path that starts and ends at the same vertex. For example, if you imagine a subway system, if you travel from station A to station B, then C, and then back to A, you've completed a cycle. To understand this better, you can see the picture here in the graph. A is connected to B, and then B is connected to C, and then C is connected to A. If you complete the whole, if you complete the whole path, you've completed the cycle. So as you can, so we can simply say that a path from A to B to C is a path. Whereas if you travel from A to B to C and then back to A, it's a cycle. So understanding paths is crucial in areas like GPS navigation, where we need to find the shortest route between locations. In computer science, paths and cycles are used in network routing and circuit design. For example, in a power grid, cycles help ensure that there are backup routes for electricity distribution if one path fails. Trees and forests. A tree is a special type of graph that is connected but has no cycles. Each tree has a root node and branches leading to other nodes. One common example is a family tree, uh, where basically ancestors are at the top and descendants branch downward. Another example is the file system of a computer. Folders are nodes and subfolders of files are branches out. A forest is simply a collection of trees. Trees are widely used in computer science, essentially in data structures like binary search trees, which help with efficient searching and sorting. As you can see, an example is multiple independent organizational hierarchies. And from the picture, you can see that graphs have cycles. Trees have no cycles and are connected, but forests have neither. They have no circles and are not connected. Now, let us explore some essential notations used in graph theory. Graph representation. A graph is written as G of VE, where V of G is a set of vertices and E of G represents the set of edges. Order and size. The order of a graph is the number of vertices, denoted as mod of V of G. The size of a graph is the number of edges, denoted by mod of E of G. Degree of a vertex. This is represented with DEG, dig of V, the number of edges connected to a vertex V. In a directed graph, we define in degree and out degree, as in incoming degrees and outgoing degrees. Adjacency. Two vertices U and V are adjacent if there is an edge between them, written as U dash V. Uh, this dash is usually represented as tilde operator. And paths and cycles. A path P of n is a sequence of vertices connected by edges. A cycle C of n is a path that starts and ends at the same vertex, like we discussed before. These notations help us describe graphs precisely and analyze the properties mathematically. To work with graphs efficiently, we need to structure them in a structured way. There are three main ways to store graphs in a computer. Adjacency matrix. A 2D table where a 1 or weight represents an edge between two vertices. This method is fast for checking connections but uses a lot of memory for large graphs. Adjacency list. Each vertex has a list of its connected neighbors. This is more memory efficient for large sparse graphs. And lastly, edge list. A simple list of all edges. This is useful when we only care about connections and not specific structures. Each representation has advantages depending on the problem being solved. Graphs are everywhere. Let's look at some other real world examples. Social networks. Platforms like Facebook, LinkedIn use graphs to suggest friends based on mutual connections. Google PageRank. Google search algorithm ranks websites using a graph of links between pages. Navigation systems. GPS and Google Maps use graph algorithms to find the fastest route. As you can see, this is a picture or a picture of a graph that represents a GPS. Biology. Graphs model protein interactions and genetic networks. These are just a few ways graphs impact our daily lives, often behind the scenes. To summarize, we've covered the basic structure of graphs, the different types of graphs like directed, weighted, and bipartite graphs, important graph terminology including paths, cycles, trees, and forests, how graphs are represented in computers. Finally, we saw real world applications in social networks, search engines, and navigation systems. So, finally, we can see that graphs are a powerful tool, and understanding them can open doors to many fields, from artificial intelligence to network security. Thank you all for your attention and time. I hope you have a very nice day.